All right, this is Unit 1, Lesson 3, Piecewise Defined Functions. So our lesson essential question is, how do you model a situation in which a function behaves differently over different parts of its domain? So at the end of this lesson, we'll be able to graph and interpret piecewise defined functions. All right, example 1, model with a piecewise defined function. Alani has a summer job as a lifeguard. She makes $8 per hour for up to 40 hours each week. If she works more than 40 hours, she makes 1.5 times her hourly pay, or $12 per hour, for each hour over 40 hours. How could you make a graph and write a function that shows Alani's weekly earnings based on the number of hours she worked? So first, we're going to make a table of values and a graph. So for 20 hours, she gets 160 up to 40. And then remember, she earns $12 per hour after she works 40 hours. So she gets 320, 380, 440, and 500. And I graph those points. So from the red line, that's up to 40 hours. And then after 40 hours is the green line. Step 2 is I notice that the plot contains two linear segments with a slope that changes slightly at x equals 40. A function that has different rules for different parts of its domain is called a piecewise defined function. I write an equation for each piece of the graph. When x is greater than 40, Alani's pay is p of x equals 8 times 40 plus 12 times x minus 40, or p of x equals 12x minus 160. Okay, so when it's greater than $40, remember she earns the $8 for the 40 hours, plus $12 for each additional hour she works. So if she works 41, she'd earn an additional $12. Okay. So what they did was they did 8 times 40, and then they distributed the 12 to the x and the 40, and then simplified it. So we get 12x minus 160. So when 0 is less than or equal to x is less than or equal to 40, Alani's pay, p of x, is $8 per hour times the number of hours she worked, or 8x. So Alani's weekly earnings can be represented by the function p of x, 8x, 0 less than or equal to x less than or equal to 40, and 12x minus 160 when x is greater than 40. This notation is used for piecewise defined functions to indicate the different functions at different parts of the domain. Okay. So let's go ahead and try. Alani has a summer job as a lifeguard. She makes $8 per hour for up to 40 hours each week. If she works more than 40 hours, she makes 1.5 times her hourly pay, or $12 per hour for each hour over 40 hours. So I want to know how much Alani earns if she works 37 hours. Okay. Well, she works 37 hours. That's under the $40. That's between 0 and 40. So I just multiply 37 times 8. So she worked 37 hours at $8 an hour. Well, that gives me 296. Okay. For B, she worked 43 hours. So more than the number of hours she works at her normal rate. So 43 minus 40 is 3 hours. So she works 3 hours over the $40, or 40 hours. So I need to do 8 times 40 plus 12 times 3. Okay, so this is the $8 for 40 hours. That's the normal amount she gets paid. She gets paid $8 for up to 40 hours of work. Anything over that, remember, she earns $12 per hour. So she worked 3 more hours than her normal 40. So she gets an additional $12 for those 3 hours, for each of those hours. So 8 times 40 is 320, plus 12 times 3 is 36. And when I add those together, I get 356. So she earned $356. All right, example 2. How do you graph a piecewise defined function? F of x equals 4x plus 11 from -10 less than or equal to x less than -2, x squared minus 1 from -2 to 2, and then x plus 1 from 2 to 10. What are the domain and range? Over what intervals is the function increasing or decreasing? So the first thing I want to do is I want to sketch the graph of y equals 4x plus 11 for values of x between -10 and -2. So here at -10, here to -2, created my line. Then I want to sketch the graph of y equals x squared minus 1 for the values x between -2 and 2. So -2, 2. Okay, here's my graph. Then I want to sketch the graph of y equals x plus 1 for values between 2 and 10. To determine the range, I calculate the y values that correspond to the minimum and maximum x values on the graph. For this graph, these values occur at the endpoints of the domain or of the piecewise function, -10 to 10. So I evaluate y equals 4x plus 11 for x equals -10. Okay, so remember, this is x equals -10, so this is why I'm using that. I substitute -10 in and solve, which gives me -29. So as I can see, -10 is down here near -29, okay? And then 10 was my maximum, and that was for x plus 1. Okay, so I substitute 10 in for the x plus 1. Well, 10 plus 1 is 11. I can see when I graph, here's 10, 10 below them. Okay. So the range is -29 is less than or equal to y, which is less than or equal to 11. The domain is my x values, okay? So my smallest x value to my largest x value, which we already learned, was -10 to 10. They told us that in the problem. So that's my domain. The function is increasing from -10 to -2. So I can see I'm going up until I get to -2. I go down and 0 to 10. So my pen's going downwards, or my marker's going downwards until it gets to 0, and then it starts going back up and it continues back up. Okay, so this down, this is a decrease from -2 to 0. All right, so I want to graph the piecewise defined function. What are the domain and range? Over what intervals is the function increasing or decreasing? So I have 2x plus 5 from -6 to -2. So I'm going to ignore everything else, and I'm just going to graph that portion. Okay. So I'm going to substitute in -6. 2 times -6 is -12, plus 5 is -7. So at -6, -7, which is about right here. Okay. And then I'm going to substitute in -2. So 2 times -2 is -4. -4 plus 5 is 1. So at -2, right around here. Oops. Okay. So when I'm going to graph this, okay, so we said for -6, it was around -7, which is right about there, and then around -1. Okay, and then I'm going to create a line from here to here. Okay. All right. Now for the second part, so that took care of this one. For the second part, I have 2x squared minus 7 from -2 to 1. So I'm going to substitute in -2. So -2 squared is 4. 4 times 2 is 8. Minus 7 is 1. So it's right here. Okay. From and then 1. So 1 squared is 1. 1 times 2 is 2. 2 minus 7 is negative 5. So at 1, I'm at negative 5, which is right here. So I start here. Okay. And I'm going to substitute 0 and see what I get. So that's negative 7, which is down here. So it looks something like that. Okay. All right, and then I have the last one, negative 4 minus x for between 1 and 3. So if I substitute 1 in, negative 4 minus 1 is negative 5, which is right here. And then 3, negative 4 minus 3 is negative 7. So for 3, it's negative 7, which is right here. Okay. Oops. There. Okay. So here is my graph. So I want to figure out my domain and my range. Well, my domain are my x values, right? So negative 6 less than or equal to x is less than or equal to 3. My range are my minimum and my maximum. So my minimum is down here at negative 7. And then my maximum is here at negative 2, it looks like, when x is negative 2. So negative 2 times 2 is 4. Negative 4 plus 5 is 1. Okay. It's increasing from negative 6 to negative 2. So the red is increasing. When we get to here, green, that's decreasing. But when I get to negative 7 up to 1, it increases again. And from negative 7x to, sorry, when x is 0, 0 to 1. Okay. And it's decreasing from negative 2, 0, and then again from 1. All right, for B, I want to graph the piecewise defined function, whether domain and range, over what intervals is the function increasing or decreasing. So I have 3 from negative 4 to negative 1. Okay, so here's my first one. First one's gonna be red. Okay, so negative, it's 3. It's at 3, which is up here, from negative 4 to negative 1. Okay, so there's my line. Okay, there's an open circle. Okay, so there's an open circle here at negative 4. And a closed one at negative 1 because of the equal signs. Okay. It's negative x from 0 to 2. So here, 0. And then it goes down here to 2. So it's negative 2. And they're both closed circles. Okay. And then my last one is 3 minus x from 2 to 4. So at 2, 3 minus x is 2. 3 minus x when x is 2 is 3 minus 2 or 1. So here, and that's an open circle. That's a really bad open circle. Try that again. Okay. And then to 4, 3 minus 4 is negative 1. So negative 1 is right here. Okay. And then I have a line between them. Okay, so that's my function. My domain is negative 4 is less than x is less than or equal to negative 1. Okay, there's nothing between negative 1 and 0, so it stops there. And then 0 is less than or equal to x is less than 4. Okay, so there's actually two sections of my domain. So my first domain is this one right here, negative 4 to negative 1. Okay, you can see that there's nothing here between those two. Okay. My range is going to be from negative 2. So my lowest is negative 2. And then LEQ. No. Yes. Y. And then up to 1. Okay. And then there's a break. And then 3. There's nothing between here and 3. Okay, but it's negative 2 is less than or equal to, because there's a closed circle here, y is less than open circle 1. And then, of course, 3, which is up here. Okay, it's increasing nowhere. This isn't an increase. This is just a straight line. So nowhere, and it's decreasing from here to here and from here to here. So it's decreasing from 0 to 2. So 0 less than x less than 2. And from 2 to 4. All right, example 3, write a piecewise defined rule from a graph.
What is the rule that describes the piecewise defined function shown in the graph? There are 3 separate linear pieces that make up the function. You can find the function and domain for each linear segment, then combine them to write the rule for the piecewise graph. Start by finding the domain for each segment. Segment A begins with a closed point at x equals negative 2. A closed point means that x equals negative 2 is included in the domain. Segment A ends at x equals 1 with an open point. An open point means that x equals 1 is not included in the domain. So the domain of segment A is from negative 2 up to, but not including, 1. Segment B begins with a closed point at x equals 1 and ends with a closed point at x equals 5. So the domain of segment B is from 1 to 5. Segment C begins with an open point at x equals 5 and ends with a closed point at x equals 8. The closed endpoint of segment B covers over the open start point of segment C, so the domain of segment B is from x greater than 5 up to 8. Next, use points on each line segment to identify the slope of the function. For segment A, the points are -2, -10, and 1, and -1. That's a change of 9 in y and a change of 3 in x. The slope is 3. For segment B, the points are 1, 4, and 5, 8. That's a change of 4 in y and a change of 4 in x. The slope is 1. For segment C, the points are 5, 8, and 8, 8. There is no change in y over the change in x. The slope is 0. Use the slope-intercept formula to solve for the y-intercept of each function. For segment A, use the point -1, 1, and the slope of 3. The y-intercept is at -4. For segment B, use the point 1, 4, and the slope 1. The y-intercept is at 3. For segment C, use the point 5, 8, and the slope 0. The y-intercept is at 8. Use slope-intercept form to define the function for each segment. Combine the functions and domains for each section to write the rule for the graph of the piecewise function. The piecewise function that describes the graph is f of x equals 3 times x minus 4 when -2 is less than or equal to x less than 1. X plus 3 when -1 is less than or equal to x less than or equal to 5, and 8 when 5 is less than x less than or equal to 8.
All right, so what rule defines the function in each of the following graphs? So I have piecewise function. So again, I'm going to create. So at my first section, I have from -5, closed, to -2. Okay, that's there's no slope, and it's at 7. Okay. My second section is from -2 to 3. Okay. So at -2, -2, 7, and 3, 2. Those are my 2 points. So to find the slope, 2 minus 7. So 2 minus 7 divided by 3 minus -2 equals -5. over 5, which equals -1. So that's my slope. And it crosses the y-intercept at 5. So at -2, 3, I have -x plus 5. And then my last one is at 4, and it's open, closed circle to 6, 4 to 6. My 2 points are 4, 5, and 5, 9. So my slope is going to be 9 minus 5 over 5 minus 4, which equals 4 over 1, or 4. My there is no y-intercept, so y equals 4x. Sorry. Four, 5. Oops, that's 6, 9. That's 6. That's 2. That's 2. 2x. Okay, so 2x. I can substitute that in to figure out. So I'm going to put, let's use 4 and 5. So 5 equals 2 times 4 plus b. So 5 equals 8 plus b. So -3 equals b. So that's my intercept. So I have 2x minus 3. So I have f of x equals, all right, so f of x equals 7. So remember way back up here, 7. -5 is less than or equal to x. It's less than or equal to -2. -x plus 5 if -2 is less than x, less than or equal to 3. Remember that one was up here. And then my last one is 2x minus 3 if 4 is less than x is less than or equal to 6. Okay. So we have, again, 3 different functions, so 3 different domains. So the first domain is from -3 to -2, and then I have -2 closed circle to 1, it's an open circle, and then I have 1, again closed circle, x, closed circle to 2. So those are my 3 domains. Okay. So looking at this one's easy because it's a straight line, so it just crosses at 1. So this is 4. Okay. For this one, I'm going to pick 2 points, which are negative. Oops. Apparently, it's not going to cooperate. So I'll come down here. So my first point is -3, 3, and then my second point is -2, 2 to figure out my slope. So that becomes 2 minus 3 over -2 minus -3. So this equals -1 over -2 plus 3, which is 1. So my slope is -1. So I have y equals mx plus b. So 3 equals -1 times -3 plus b. So 3 equals 3 plus b. So b equals 0. So y equals -x is my first one. For my second one, let's pick the points 1, -1, and 2, 3. So my slope is going to be 3 minus -1 over 2 minus 1. So that's 3 plus 1, or 4, over 1, which equals 4. So y equals mx plus b. So I have -1 equals 4 times 1 plus b. So -1 equals 4 plus b. So -5 equals b. So y equals x minus 5. All right, so I have for f of x equals -x if -3 is less than or equal to x is less than -2. 1 if -2 is less than or equal to x is less than 1. And 4x minus 5 if 1 is less than or equal to x is less than or equal to 2. All right, I want to write a rule for an absolute value function. For example, 4, how can you rewrite the function f of x equals the absolute value of 6x plus 18 as a piecewise defined function? So the first thing I want to do is write the function in the form f of x equals a times x minus h plus k to find the vertex of the function. So f of x equals the absolute value of 6x plus 18. I can factor out a 6 from that, so I get x plus 3. So 6 goes outside. 6 times the absolute value of x minus -3 equals 0. So the vertex is h of k equals -3, 0. The graph has 2 linear pieces, one to the left of x is -3 and one to the right of x is -3. So determine the slope and equation of each piece of the function by testing x values on either side of -3. So from at -4, 6, my slope's -6, so my equation is y equals -6x minus 18, and to a point that's greater than -3, we pick 0, 18, which was 6, so y equals 6x plus 18. So I write a piecewise defined function. The absolute value function, f of x equals the absolute value of 6x plus 18, can be written as the piecewise defined function f of x equals -6x minus 18 when x is less than -3, and 6x plus 18 when x is greater than or equal to -3. Okay. Confirm by graphing, the vertex is at -3, 0. All right, so how can you rewrite each function as a piecewise defined function? I have f of x equals the absolute value of -5x minus 10. So f of x equals absolute value -5 x plus 2. Okay. So, but I want to, again, like I said over here, we want to rewrite it as f of x equals a, x minus h plus k. So this is going to give me f of x equals 5 times x minus 2. That's negative 2 plus 0. Okay. So I'm going to end up with negative 2, 0, like this one. Negative 2, 0 is my vertex. Okay, so when I'm writing this, I have f of x equals negative 5x minus 10 if x is less than negative 2 and 5x plus 10 if x is greater than or equal to negative 2. For b, I have f of x equals negative absolute value of x plus 3. So I have f of x equals x plus 3 if x is less than 0 and negative x plus 3 if x is greater or equal to 0. It's actually really helpful if you graph these. If you graph the function, you can see it. Example 5, graph a step function. The shipping cost of items purchased from an online store is dependent on the weight of the items. The table below represents shipping cost y based on the weight x. Graph the function. What are the domain and range of the function? What are the maximum and minimum values? So the weight of items is 0 less than x less than or equal to 2 pounds, and 2 less than x less than or equal to 4 pounds, 4 less than x less than or equal to 6 pounds, and 6 less than x less than or equal to 8 pounds. Shipping costs $5, $8, $11, and $14. So the graph of a function looks like a steps of a staircase. This is called a step function since it pairs every input in an interval with the same output value. So each y value goes with a set interval of x values. So for example, y equals 5 for 0 to 2, and y equals 8 for 2 to 4. A closed circle means that the x value is included in that domain and the less than or equal to or greater than or equal to sign is used. An open circle means it's not included. So domain x is from 0 is less than x is less than or equal to 8. So again, closed circle to open, or open circle to closed circle. And my range are 5, 8, 11, and 14. 6 isn't included because it's not my range. 7's not. So this function has a minimum of 5 and a maximum of 14. All right, so let's try it. The table below represents fees for a parking lot. Graph the function. What are the domain and range of the function? What are the maximum and minimum values? Okay, so my domain of the function is from 0 is less than t is less than or equal to 12. My range are just my y values, so 10, 15, 20, 25. My maximum values is 25, and my minimum value is 10. So when I graph this, all right, so when I graph this, I start at 0. So from 0 to 3. So 0 to 3. My cost is 10. From 3 to 6, my cost is 15. So open circle, close circle, line. Okay. Then from 6 to 9, so 6, 9. The cost is 20. And then from 9 to 12, my cost is 25. So there's my. All right, so concept summary, piecewise defined function. In words, a piecewise function has different rules for different parts of its domain. So basically, it's like putting all these little functions together into one function. So in algebra, this is what it looks like. And here's my graph. So at 7, it's a straight line from -5 to -2. For f, or 5 minus x, the blue, from -2 to 3. And then the green, 2x minus 3 from 4, open circle, to 6, closed circle. And that is the end of Unit 1, Lesson 3.